Hi friends! Today we will learn about concave lenses. So let's get started. Friends, you might have seen that people with poor eyesight wear spectacles to see better. The glasses used in the spectacles are examples of lenses. A lens is a transparent and curved piece of glass or any other transparent material. Now, let's discuss the concave lens. Concave lenses have two spherical surfaces that curve inwards. A concave lens is thicker at the edges but thinner than the middle. Concave lenses were discovered by Nicholas of Cusa back in 1451. Now, let's discuss the various terms related to the concave lens. The first term is the center of curvature. Concave lenses have two spherical surfaces. Let's name them as spherical surface 1 and spherical surface 2. Spherical surface 1 is part of the sphere and has center C1, and spherical surface 2 is part of the sphere and has center C2. The centers of these spheres are called centers of curvature of the lens. The center of curvature of a lens is usually represented by the letter C, and since there are two centers of curvature, we denote them as C1 and C2. Therefore, we learned that the centers of spheres of which the two spherical surfaces of the lens are parts of are called the centers of curvature. The next term is the optical center. The center point of a concave lens is called its optical center. It is usually denoted by the letter O. The third term is the radius of curvature. The distance between the optical center and the center of curvature is called the radius of curvature. The following term is the principal axis. The straight line passing through the optical center and the two centers of curvature is called the principal axis. The next term is the focal point. Several rays of light parallel to the principal axis fall on the concave lens. These rays, after refraction from the lens, diverge, which means that the light rays move away from each other. The diverging rays of light, when produced backwards, meet at some point on the principal axis. This point on the principal axis is called the focal point, or the principal focus of the lens. Or it is also sometimes called the focus. So, we learned that the focal point or focus of the concave lens is a point on the principal axis at which parallel rays of light appear to diverge. The focal point is usually denoted by the letter F. Just like there are two centers of curvature, there will also be two focal points, one on each side of the lens, and we denote them as F1 and F2. Concave lenses are also called diverging lens because when parallel rays of light pass through the concave lens, the refracted rays diverge. Now we will learn some rules for determining the image formation in the case of concave lenses using a ray diagram. A ray of light parallel to the principal axis refracts and appears to diverge from the principal focus located on the same side of the lens. Let's repeat. A ray of light which is parallel to the principal axis refracts and appears to diverge from the focus, which is located on the same side of the lens. Here's the second rule. A ray of light directed towards the focus on the other side of the lens refracts and emerges parallel to the principal axis on the other side of the lens. Let's repeat. A ray of light directed towards the focus on the other side of the lens refracts and emerges parallel to the principal axis. This is the third rule. A ray of light passing through the optical center of the concave lens emerges without any deviation. This is the same as a convex lens. Recall that in a convex lens, a ray of light passing through the optical center also emerges without any deviation. These are the three rules we will use while learning the image formation in the case of a concave lens. Remember, concave lenses always give a virtual, erect, and diminished image. Diminished image means that the image will be smaller than the size of the actual object. And a virtual image means that the rays of light coming from the object will not meet at any point. They will only appear to meet. Now, let's revise the difference between a real and a virtual image. A real image is the image which is formed when the light rays meet at a particular point. And a virtual image is the image which is formed when light rays appear to meet at a point but do not actually meet. In the case of a real image, light rays actually converge at a certain point. In the case of a virtual image, light rays are perceived to converge at a particular point. However, they do not actually converge. A real image is always inverted. That is, the image formed is upside down. And a virtual image is always going to be upright. Real images can be projected onto a screen, but virtual images can never be projected onto a screen. Images formed in the plane mirror are always virtual. So, the image is formed in the virtual world, and you can never touch that image. Whereas, the images formed on the screen of a cinema hall using the projector are real images. So now, we have learned what real images and virtual images are. We also know that in the case of a concave lens, images formed will always be virtual and diminished. Now, let's learn about image formation in the case of a concave lens. We will consider three rays. A ray of light parallel to the principal axis. After refraction, this ray will appear to diverge from the focus. A ray of light directed towards the focus will emerge parallel to the principal axis. Finally, a ray of light passing through the optical center will emerge without any deviation. Different images are formed depending on the distance of the object from the lens. With the convex lens, we studied 6 different positions of the object. In the case of a concave lens, there are only 2 positions. The first case is that the image can be located at infinity. The second case is that the image can be formed at any location between infinity and the optical center. In all the cases, the image form will be diminished and virtual. Here is the first case. In this case, the image will be at infinity, or at a great distance from the center of curvature. So, the rays formed from the object AB will be parallel to the principal axis, and they will diverge along the directions OX and OY, and will appear to meet at F1. So, the image produced will be at F1, as the light rays do not meet but appear to meet at point F1, and the image formed will be highly diminished or point-sized, virtual, and upright. Our second case is when the image AB is placed anywhere between infinity and the optical center of the concave lens. The light rays parallel to the principal axis diverge along the direction mx after refraction and appear to come from the principal focus f1. And the light ray that passes through the optical center goes without any deviation along the direction OY. So, both the light rays diverge but appear to meet at the point A'. By drawing a perpendicular line from A' to the principal axis, we get the point B'. The image formed is A', B'. It is virtual and diminished, and we know that virtual images are erect or upright. Now, let's see the various locations of the object between infinity and the optical center of the lens and its effect on the imaged form. We place the object beyond the center of curvature. A highly diminished image is formed. Now, bring the object a bit closer. And a slightly bigger image will be formed. Now bring the object more closer to the lens. And once again, a slightly bigger image is formed. Bring the object more closer again, and the image is even more bigger. Now, bring the object even closer, and the image is even more bigger. We observe that if we place an object anywhere between infinity and the optical center, the imaged form will be virtual and diminished. And as the distance between the object and the lens decreases, the size of the image increases. Now friends, can you answer why concave lenses are called diverging lenses? Of course! It is because of its ability to diverge a parallel beam of light to a single point. Now, let's revise the image formation in the case of a concave lens. If the object is placed at infinity, the image is formed at the focus. The image is a highly diminished, point-sized, virtual image. If the object is placed anywhere between infinity and the optical center of the lens, a virtual diminished image is formed between the focus and the optical center of the lens. The closer the object is to the lens, the bigger the image is. Now, let's discuss the uses of a concave lens. Concave lenses are used in spectacles, flashlights, the peephole of a main door, and finally binoculars. Concave lenses are also used to correct myopia, which is an eye defect. A person suffering from myopia can see nearby objects clearly, but faraway objects are blurry. Myopia is also called nearsightedness or short-sightedness. Concave lenses are also used in cameras. Camera manufacturers use the combination of concave and convex lenses to improve the quality of photographs. So, we have learned about both concave lenses and convex lenses. We will now discuss the power of a concave lens. In our last lesson, we learned that the power of a lens is defined as the ability of a lens to converge or diverge light rays. And the power of a lens depends upon the focal length of the lens. It is the reciprocal of its focal length. As the focal length becomes shorter, the divergence and power of the lens becomes greater. In other words, if you increase the focal length, the power of the lens decreases, and if you decrease the focal length, the power of the concave lens increases. So, it is the reciprocal of the focal length. The power of a lens is denoted by the letter P. The power of a lens of focal length f is given by P equals 1 over f. The SI unit of power of a concave lens is diameter, and the SI unit of focal length is meter. So friends, we have learned a lot about the concave lens.
Thank you so much for watching. Don't forget to like, comment, and share this video. And if you want to see more fun videos, you can hit that subscribe button. You can also follow us on Facebook and Instagram for more content. Bye-bye!